Scientists have a saying when they study Mars: follow the water. Find where water once was. And you might find something else. Something that changes everything. For decades, this was theory. Educated guessing from orbital photographs. Models built in supercomputers. Scientists arguing over what old photos from space actually meant. Then in January 2026, a team led by a PhD researcher at Imperial College London published a paper in the Journal of Geophysical Research. And the debate, a debate that had been running for years, was settled. Perseverance had found a beach. Not a metaphor, not an analogy, an actual ancient shoreline, with wave-polished rocks, with rounded grains, with the geological fingerprints of water lapping against a crater rim 3.5 billion years ago, on a planet that today is cold, dry, and dead. The proof of water on Mars isn't a theory anymore. It's sitting in the rocks, and this is what it took to find it. Let's start with what we actually knew before the rovers arrived. From orbit, Mars looks scarred by water. The surface is covered with what appear to be ancient river valleys, dried lake beds, canyon systems carved by something that flowed for a very long time. The Mars Reconnaissance Orbiter detected clay minerals in certain craters, and clays only form when rock spends extended time in contact with liquid water. But orbital photography is not proof. It's suggestion, implication. The debate between scientists was real and it was serious. Some researchers thought Mars had been warm and wet for millions of years, an early climate rich enough in greenhouse gases to sustain oceans, rivers, rainfall. Others thought Mars was mostly frozen, with occasional melts during volcanic eruptions or asteroid impacts. Others thought the canyon systems were carved by something else entirely: lava flows, glaciers, processes that don't require liquid water at all. Without boots on the ground, or at least wheels, you couldn't settle it. The rovers were sent to settle it. And what they found, over 25 years of missions, across multiple craters, in rock after rock after rock, is that Mars was not just damp. It was genuinely, extensively, persistently wet, for longer than scientists had expected. In conditions that, by every measure we have, could have supported life. Here is the evidence, discovery by discovery. The first major breakthrough came not from a new mission but from a moment of patience. NASA's Opportunity rover had been driving across Mars for years, far beyond its original 90-day mission, when it reached the rim of a massive crater called Endeavour. The crater was chosen because orbital data showed clay minerals nearby, clays that required liquid water to form. What Opportunity found in the rock exposed at the crater rim changed the mission's entire significance. A thin white vein running through the darker surrounding rock. They named it the Homestake deposit. Analysis identified it as gypsum, calcium sulfate, a mineral that forms when water dissolves calcium out of rock, carries it through underground fractures, and deposits it as a vein when the water eventually evaporates. This is not surface water. This is water moving underground, through fractures, deep enough to be protected, long enough to leave a record that survived 3.5 billion years of Martian erosion and radiation. And the water was not acidic, not the harsh, chemistry-hostile kind that would have been hostile to life. It was closer to neutral pH, the kind that, on Earth, produces springs where life flourishes. Steve Squires, the principal investigator for the Opportunity mission, said it was the most unambiguous evidence for liquid water on Mars collected up to that point. Unambiguous. That word matters in science. It means, this is not a stretch. This is real. In February 2021, Perseverance landed inside Jezero crater, a 45-kilometer-wide impact basin in Mars's northern hemisphere. From orbit, Jezero looked like a former lake. There was a visible delta, a fan-shaped deposit of layered rock, where a river had once flowed into standing water, exactly the way rivers form deltas on Earth. Scientists believed a lake had once filled Jezero to a depth of perhaps 100 meters. Believed. The RIMFAX ground-penetrating radar on Perseverance settled it. By sending radio waves into the ground and measuring how they bounced back from underground boundaries between rock layers. RIMFAX revealed sedimentary layers buried up to 35 meters below the surface. Layered the way water deposits sediment, horizontally, in sequence, building up over time. The study, led by UCLA and the University of Oslo, confirmed it. Those layers were deposited by water flowing into Jezero from the ancient river system, exactly as hypothesized. Not lava. Not glaciers. Water carried sediment, building up at the bottom of a lake that existed 3.7 to 4.2 billion years ago. But Perseverance didn't stop there. While exploring the floor of Jezero, the rover found something unexpected in the deepest rocks: igneous rock. Olivine, formed by volcanic cooling, not water. Initially, this seemed like bad news. If the floor of the crater was igneous, where was the lake sediment? The answer: above it. Water came after the volcanic activity cooled. The lake formed on top of ancient lava flows, and that combination, mineral-rich volcanic rock, liquid water, time, is exactly the chemistry that produces the conditions most favorable for life. As Perseverance scientist Joel Hurowitz of Stony Brook University put it, the combination of chemical compounds we found could have been a rich source of energy for microbial metabolisms. Not could be life. A rich source of energy for metabolisms. The distinction matters. The chemistry was there. Now let's talk about the discovery that changed everything. January 26, 2026. Perseverance had spent nearly a year exploring a geological feature called the margin unit, a band of carbonate-rich rocks lining the inner rim of Jezero crater. Scientists had debated this unit for years. Some thought it was sedimentary, deposited by the ancient lake. Others thought it was igneous, formed underground and later altered by water. The paper led by Alex Jones at Imperial College London settled it definitively. It was a beach. The rocks in the margin unit contain rounded grains, sand grain-sized particles polished smooth by wave action. The kind of rounding that only happens when rock fragments tumble repeatedly in moving water. The kind of rounding found on every beach on Earth. Beneath those rounded grains, the bedrock shows signs of hydrothermal alteration, underground water circulation, driven by heat from below, chemically changing the rock over millions of years. Professor Sanjeev Gupta of Imperial College noted, this underground hydrothermal environment is known to support microbial life on Earth. And then surface water arrived. Waves from the ancient Jezero lake struck those already altered rocks, breaking them down further, depositing the rounded sandy layers that Perseverance photographed in 2023 and 2024. The beach lies stratigraphically below the famous Jezero River Delta, meaning it is older. Which means stable, habitable lake conditions existed at Jezero for longer than scientists previously thought. Alex Jones, the lead author, said it plainly: shorelines are habitable environments on Earth, and the carbonate minerals that form here can naturally seal in and preserve information about the ancient environment. A sealed record of a beach on Mars, 3.5 billion years old. The beach finding was not the only discovery published in early 2026. In January 2026, a separate team from Purdue University published research on strange bright white rocks that Perseverance had been photographing since it landed. These rocks, scattered across Jezero crater, without any obvious source, turned out to be kaolinite. A white clay mineral, kaolinite forms under very specific conditions. It requires not just water. It requires millions of years of heavy rainfall in a warm, humid climate. On Earth, kaolinite forms in tropical rainforest environments, places where rainfall is consistent, heavy, and sustained over geological time. The presence of kaolinite on Mars does not suggest occasional melting. It suggests extended, warm, wet climate conditions that persisted for millions of years. The lead researcher from Purdue noted that there is no obvious nearby source for the kaolinite. It appears scattered across the rover's path, suggesting it was deposited widely, not locally produced. Wide distribution of a rainfall indicator mineral across a crater that also has a beach and a river delta is not a coincidence. It's a picture. Mars had rain. Mars had beaches. Mars had rivers flowing into lakes. Mars had underground water heating rock for millions of years. All at the same place. All at roughly the same time. All 3.5 billion years ago. And then there is the sample NASA hasn't been able to study yet. In July 2024, Perseverance was exploring a formation called Bright Angel, rocky outcrops on the edge of Neretva Vallis, an ancient river valley that once fed water into Jezero. The rover drilled into a rock called Chayava Falls and extracted a sample designated Sapphire Canyon. After a year of analysis using instruments on board, PIXL and SHERLOC, two of Perseverance's most sophisticated instruments, scientists published a paper in Nature in September 2025. The rock contains carbonate minerals and organic compounds. It shows unusual textures. It contains chemical signatures that could indicate. The word NASA used carefully was could ancient microbial life processes. NASA describes it as the mission's best candidate for containing signs of ancient microbial life. Their description, the clearest sign of life yet found on Mars. Hurwitz was direct, but just because we saw all these compelling chemical signatures in the data didn't mean we had a potential biosignature. We needed to analyze what that data could mean. To determine whether those signatures are biological or non-biological in origin, to truly know whether they are evidence of life, the sample needs to come back to Earth. To laboratories with instruments that can perform analysis no rover can replicate. And here is where the story becomes genuinely painful. The Mars Sample Return Mission, the one designed to retrieve Perseverance's samples and bring them to Earth for analysis, was effectively canceled in 2025 when NASA's science budget was cut by 47% under the Trump administration's fiscal year 2026 budget proposal. Congress passed a bill securing general NASA funding, but the Mars Sample Return Program was specifically excluded. The Sapphire Canyon sample, the beach rocks from the margin unit, the olivine cores from the ancient volcanic floor, 30 samples in total, collected by Perseverance over 4 years of careful work. Sitting on Mars, waiting. Everything we've found on Mars says those conditions existed. The samples are there, the evidence is preserved. The carbonate minerals have sealed whatever was in that ancient shoreline for 3.5 billion years. We just need to go and get them.